We are testing how dark matter might interact in a crystal detector. So this is a beamline where we do experiments with the accelerator here, and we generate neutrons to create nuclear recoils in a crystal detector that normally sits here. And we do that to try and use the neutrons as a surrogate for dark matter, right? Because we want to understand how dark matter might interact in a crystal detector.
Okay, so we're pretending it's dark matter.
Yeah, that's right. I mean, at the short scales that we have here, the neutrons can generate the same sorts of interactions that we would expect to see in a dark matter detector. Which is
not that we know what dark matter is.
No, we don't.
But we're taking a guess.
Yeah, we're having it's an educated guess, but yes, it's a guess.
I guess it's at least neutral, so we know that.
That's the key property, actually, right? Yeah. So it can go into the detector, generate an isolated nuclear recoil from scattering, and then leave the detector, much like a dark matter particle would.
Okay, right. Okay, so particles, you're making neutrons in there.
Yep.
And they come out into these different detectors here.
Yeah, that's right. These are detectors, they're liquid scintillator detectors.
Yep.
So when the neutrons come and they
scintillation means a flash?
Scintillation means that when a particle deposits energy, it will give a little flash of light.
Yep.
Right. And so these liquid scintillators will measure those neutrons that come scattering off our crystal detector.
Right.
And so they're at, our neutrons are at a fixed energy. These are at defined angles, which defines the energy of the nuclear recoil that we see in our detector.
So it's kind of billiards.
Yeah.
Balls bounce off and go at different angles.
Much like billiard balls, yeah.
Right. And if you get the angle just right, it goes in the pocket.
Exactly.
Yep. Okay. So is this what's going to be in your dark matter detector?
So the dark matter detector will be sodium iodide. That's the bit that's actually looking for dark matter.
Tell me a bit about that. Where's that going to be?
So this is a detector that we're building to go into a new underground laboratory in Stawell in Victoria.
Yep. Right.
So it's going to be 1 kilometre underground in a gold
big hole
mine.
To dig. Oh, right.
It's in an existing gold mine, right? Yep. So we don't have to dig the hole. Yep. But it's going to be. We need to go that deep to try and cut out all the backgrounds from cosmic rays that are constantly bombarding the Earth, right? Right. So we're looking for very, very rare events.
Yep.
And if we were to conduct the experiment on the surface, then we would just be drowned out by all these cosmic rays. So we need to go very, very deep where we can get a lot of rock above us to shield these high energy particles. Yeah. So we're building this detector to go in there. It's going to be very, very ultra pure sodium iodide crystals that are sitting within another detector. So this liquid scintillator veto detector around the sodium iodide.
Yeah. What's a veto detector?
So the purpose of the veto is to try and catch events that are that might look like dark matter otherwise, right? So some particle events, like from neutrons, say, could interact in the detector, look like dark matter, scatter out of our sodium iodide crystals, and what we use our veto for is to look for those particles interacting again, right? Because dark matter would be only weakly interacting, so we expect it to only interact once, right? And so having a veto lets us say, well, that was just an ordinary particle. We can ignore that one.
So if it were a neutron, it might, you hope, interact once in the liquid around it, and then again when it gets into the sodium iodide.
That's
then because you should say, it's interacted twice, is probably not dark matter.
That's right. Yeah.
Right. Yeah. So basically what you're doing is building a detector that finds things that hardly ever detect, that hardly ever,
Yeah, we're looking for really rare events.
It's a kind of backwards thing, isn't it?
Yeah. There's and most dark matter detectors measure nothing, right? So we may end up only setting a limit, right? Although we are testing a particular experiment, that has claimed to detect something.
Oh, okay.
So there's an experiment, and this is the only experiment that has claimed to detect dark matter.
Yep.
No one has, really thoroughly tested this claim yet, right? And so we're essentially going to repeat the experiment and see if we see the same thing.
Yeah.
Okay.
And so how long I presume you need to leave it sitting there for a long time.
Yeah.
And then at the end of that, you say, we didn't see anything.
Yeah, that's right. Yeah. So we think
we did see something.
Well, if we see something, it'll be fantastic, right? But we're planning to run for about 3 years.
3 years.
Right. So we think in 3 years we can do a test of this other measurement, and say yes, they're definitely seeing something real, or no, they're not.
So So what's, if they're correct, what is a dark matter particle then? What tell me, we actually might know what dark matter is?
Sure, yeah. I mean, it would be the first step on a long journey of understanding a lot about these particles. But if this other measurement is correct, then dark matter is a weakly interacting massive particle, right?
That would spell WIMP.
A WIMP. That's right.
Why did the physicists choose WIMPs as their mascot?
Oh, we like strange
Don't
names.
answer that.
Yeah. Yeah. No. So a WIMP is a very good candidate for dark matter, right? There's a lot of reasons that we might think WIMPs could be dark matter.
Yep.
You can make a big bang that includes WIMPs and ends up with dark matter that looks like what we see today when we do our observations. So it's very natural to explain, what dark matter might be.
But that's just a model, right?
But this is a theory, right? And we need to do experiments to test this theory.
Yeah.
And so, if it is a WIMP and if it is the Dharma WIMP, then we would want to do more experiments later on to test, find out all sorts of particle properties about this. What is the spin? What is the mass? Right? What is the interaction cross section? These things.
Yeah. What's your sense? Is dark matter going to be? Is it even going to have spin and I mean, it has to have mass, right?
Yeah.
Because it's gravitational. That's how we can see its effects.
Mm-hmm. That's right. Yeah, so it has to have mass.
Yeah.
We know that it can't be very strongly interacting at least with ordinary matter.
Yep.
And, there's not a whole lot else that we know, right? We know that it can't be traveling very quickly, because it's gravitationally bound to the Milky Way, right? So there's some things that we know, but there's really a lot that we don't, and it's a real mystery. And this is why it's so exciting to be in this field.
Yeah, okay. So wow, imagine if you found that first particle, or I know. So you're down to individual particles you can detect. Is that the idea?
Yeah, that's right. I mean, we would hope to measure dark matter with our experiment by actually measuring the rate of dark matter interactions changing throughout the year, right? So there's actually a modulation in the flux of the dark matter through the Earth, right? Now this arises because the Earth is part of the solar system, and the solar system's orbiting the galaxy, and that orbit creates a wind of dark matter through our solar system, right? Now the Earth going around the sun modulates that wind, right? How fast the wind is hitting us.
So sometimes we'd be...
Is
it a Doppler effect?
Well, it's just that sometimes we're going the same direction as the sun, and sometimes we're going the opposite direction of the sun. So it's a bit like a Doppler effect,
Right. Okay.
So it's the orbit of the Earth changing the velocity of the Earth through the
it's not like a shadow though. We're not going behind the sun.
No, it's not that.
Because presumably it passes through the sun.
Yeah, for the most part.
Except that the sun's a big gravitational body, so it would affect it in some way.
Yeah,
this is very confusing when you don't know what it is.
There are signals that you can look for from dark matter that's been captured by the sun, right? In the very center of the sun, you can look for neutrinos being emitted from dark matter annihilations. But this is a whole nother type of experiment.
Wow, okay.
Yeah.
Right. But for the moment, this is just a test run here.
But yeah, this is a test run. This is an important part of the understanding the energy scale of these interactions.
So what are you actually testing right here?
So we're looking at the nuclear recoils, which is the dark matter signal that we expect to see in our sodium iodide.
Yeah.
Right? So it's important to understand, how much light, what is the energy scale of these nuclear recoils.
Yeah.
And if we can understand that and we see a signal, then we can then understand things about, the properties of the dark matter that's interacting with the detector, the mass, right? Is the main one.
So hopefully it's around the mass of a neutron. And then we can...
that would be convenient.
So take me through this detector then.
Right, so this is at the front here, we have some liquid scintillator. This is a volume that sort of goes out to here also. And then there's a window, and that connects to a photomultiplier. And this is a very sensitive light detection instrument that can detect down to a single photon.
Right.
So
a neutron would come in here.
Yeah.
And cause a little flash of light.
Yes.
And then the photomultiplier would...
So that will record that flash of light, translate it to essentially a voltage, right, that we then measure and record and do some analysis later on. This is a slightly different liquid scintillator from what will go in SABRE.
Yep.
But we are actually at ANU, we're sort of developing the liquid scintillator that will go into the Veto for SABRE, right? So there's a whole experimental program.
That's not what's in here though.
But that's not what's being done here at the moment.
Right. Okay. Yeah. Okay. Right. So these are working now.
Yep.
All set. All right. Better let you get on with it then. Thank you very much.
Thank you.